We're going to continue atoms today, starting with something that I've said quite a bit the last 2 days. You just hadn't officially written it yet. So to show you what they're writing at home, go ahead and pause the video and get it into your notes real quick. You've heard me say a couple times what isotopes are. We're going to go further with it today, but just a quick reminder. The idea is that most of the elements on the table exist in multiple forms naturally out there in the world. The difference between those multiple forms of a given element, whichever one you're looking at, is mass. This one's heavier than this one. And the fact that you have one that's lighter and one that's heavier, those two samples of whatever element, iodine, maybe, those are isotopes of iodine. Two different samples, species, of the same element that exist with different masses. Get out a periodic table. I meant to say that already. My bad. Please get out a periodic table. Anybody want to come say hi to the people at home while people are getting out a periodic table? You can run up and be famous. I'm never recording my honors again. Here they come. Here they come. Are you ready? This is Jessica. This is Ariana. Anybody else want a fake name? No, I have, because not everybody wants to be permanent. And this is Adolf. Okay. It goes on Schoology. The honors videos that people have been watching, I recorded 8 years ago, so I have no gray, which I don't look wise enough. So it was just time to re-record. Yeah, I've been doing it for every lecture this year. It's just I skip between 6, 7, and 8 periods. It's going to keep happening during the school year. So you have to get brave, and I'll give you a fake name. Okay, sorry. I hope you fast-forwarded all that. Anyway. Hey, there is a phrase up here, though, that I hadn't used yet, and it's the phrase average atomic mass. Look at your table now that you have it out in front of you. Those decimal numbers that are decimals, and they kind of weird that they are, since they're made up of entire whole number particles being added together. It's an average. That's what it is. If we go back to iodine, the idea is... Now I'm getting instant messages. Okay. The idea is that if you've got your two iodines, the heavy one and the light one, instead of just averaging them together straight out, they take into account how abundant they are. Whichever one of those iodines is more common is going to pull more on the average than the iodine that's rare, which is what's happening with those decimals. My biggest job today is to get you to be able to calculate the decimals. What did the scientists do with the abundance of the different elements to come up with the decimal number that is representing each individual element? So that's what we will end with. But first, I just want to make sure that we are absolutely on the same page with our isotope data. Whoops. Got some lag going on. So let's look at rubidium together. We're going to be looking at this data here. All right, a little examination of rubidium. We're going to compare rubidium 85 to rubidium 87. In regards to protons, electrons, neutrons. The subatomic particles so these are two different isotopes of rubidium. Let's do just a general comparison. Let's go get some help, though, because I love your voices. Let's go over to cluster 5 to start off with and talk to seat 1. That was amazing that you did not get it. That was so low odds. Hey, 5-1. Can you just give me a proton count of rubidium-85? How many protons do you think he has? $85, Rod. Do you have a table out? Find them on the table. Look to the far left, and there's a different value. 37, yeah, because we know that the proton count is always equal to the atomic number. Hey, class, how many protons does this other isotope of rubidium have? Also 37, because protons give identity, so they must be the same if they're both rubidium. Let's head on over then to cluster 3, almost a full cluster, and talk to seat 1. Hey, 3-1, what about an electron count of rubidium-85? You don't got to go there for it. You're working too hard. An electron count for rubidium-85. Also 37, because we know that the only way these numbers are not the same is if it's an ion, a charge, right? If I say he's positive or he's negative, then we have to figure out, okay, well, that means the pluses and the minuses aren't the same. But I didn't go out of my way to show an ion, a charge. Protons and electrons equal. How many electrons does that other isotope have? Also 37. So the point I'm trying to make is we've got these two different species of rubidium, two different isotopes. So far, everything's the same. Because what's different about isotopes? Well, let's go talk to one more person and ask the harder question. Hey, cluster 3, seat 4, 3-4. Ryan, do you want to give me a guess on the neutron count of rubidium-85? And there's never a shame in using a calculator if you want to. You do have access. Perfect. 48. By going 85 minus 37. Hey, class, how many neutrons does the other isotope have? 50. And there's our difference. You can even think back to your marbles, right? If I gave you rubidium-85 and said, make it rubidium-87, you would just drop two more marbles into the nucleus. Because as long as the protons stay the same, it's still rubidium, but neutrons have mass. The difference between isotopes is neutron count. Yeah? Okay, that's kind of review-ish. Let's move on to the real bulk of, one thing I did want to ask you, which of those rubidiums is the most common isotope of rubidium? The 85, how do you know it's the 85? If you round the periodic table average atomic mass, it rounds to 85. So we've got common isotope, rare isotope. The lag drives me crazy. Okay. You already wrote that down. That's the equation from slide 1. Look at your equation you wrote from slide 1 at the bottom. Hey, on the equation you wrote, there is a dot, dot, dot at the end. Do you see the dot, dot, dot you wrote? What's that called grammatically? What? An ellipses. Ooh, some of y'all just got smarter. All right, the dot, dot, dot is an ellipses. Go use that in a sentence this weekend. It means could be continued, right? So if you look at this formula, which I'm about to teach you how to use, and you don't have to memorize it, I'll give you that formula on your test next Monday. But what it means is some elements on planet Earth have 2 isotopes. Some have 6. It depends on the element you're talking about. So if you're having to analyze, come up with the decimal number, the average atomic mass of an item with 6 isotopes, then you're good. The formula is just longer. You'll have to do isotope 1, and then isotope 2, and isotope 3, and it makes the equation drag out. I'll show you what I mean. Go ahead and take a look at rubidium with me, because I bet you're not sick of hearing me say rubidium yet. This is the data, that they're looking at right now on rubidium. What you'll notice is that the percent abundances are being provided. What that means is rubidium 85, if you were to go find one, go pull one out of the air outside, there's a 77% chance that it's rubidium 85 and only a 23% chance that it's rubidium 87. All right, where do they get those percentages? Decades of study. All right, that's where it comes from, environmental scientists. What I want you to know how to do is how they take that data and come up with the decimal numbers, the average atomic masses on the table. It's a simple plug and chug with a little math thing I need to make sure that you know. I need you to know how percentages talk to decimals. For example, if I were to say that I only like 65% of you, first off, that's an overestimate. Secondly, what is that number written as a decimal? 0.65. Now, if you didn't know that 65% is the same as 0.65, then shame on your 7th grade teacher for doing you poorly. But if you don't know that, then jot this down in your margin of your notes, or just jot it down anyway if you want to. To go from here to here, there's two ways to look at it. All right, you can slide the decimal that's in the percentage to the left twice and give it to you, no matter where it is. All right, it might not be right there. Wherever the decimal is, slide it to the left twice, or divide the percentage by 100. Both of them will get you there if you just haven't been trained to do that. Yes, yes. All right, yeah, let's go back to rubidium. I want to use the data given the percent abundances to find average atomic mass. Work with me, let's plug and chug together. Looking at the equation, it says isotope mass number 1. Well, that's 85. It's the mass of the first isotope. It says we're going to multiply that by its percentage, but as a decimal. You can't put percentages into this equation. It needs to be the decimal version of the percentage. How do you write 77.2% as a decimal? 0.772. There's your only little trick. And then move to the next data set. Plus, you'll notice there's a plus in the equation. Isotope number 2 is rubidium 87. Times his percentage as a decimal, 0.228. And there we go. Type it in, y'all. Let's practice on the calculator. Just type exactly what you see. We don't apply normal sig fig rules to average atomic mass. Instead, you're just going to round the number to 2 digits past the decimal, which is true for almost every element up there, except the first few. Again, when calculating average atomic mass from isotope data, just always round it to 2 digits past the decimal. With that said, does anybody want to yell out a number? 85, not 0.47, 0.46 if you round it properly. All right. Your calculator should round to that 2 digit past the decimal number. And if you got something way different, then you need to rerun the purple, because the purple's correct. It's just your fingers that are wrong. The units for average atomic mass is AMU. You need to know that. It stands for atomic mass unit. You don't have to know that. But I want you to know that AMU is units of this skill. All right, let's get Aspen involved, shall we? Next data set. We're dealing with uranium this time, but what do you notice is different in general? How many isotopes of uranium are there? There's 2. So it's just an extra data set. Let's work together still to plug and chug our 3 uranium isotopes. The first one has a mass of 234. I want to multiply that times his percentage as a decimal. Let's see if I can trick you or not. Let's go over to cluster 2 and talk to C3. I don't know why, man. All right, so it's 2, 3. Can you tell me what that first percentage is as a decimal? He said this is the number that was said, 0.0001. Do y'all like that number? It's perfect, right? Be careful with the small numbers because sometimes you have to squint a little harder. But yeah, if you slide to the left twice, there's 3 total zeros to the right of the decimal. Or just type in divided by 100 on your calculator, and you'll have less room to worry. We add the data sets together. The second isotope value is 235. Let's get another voice of the people. Cluster 3, seat 5. Dun, dun, dun. It happened. Hey, Aspen, can you tell me what that percentage is as a decimal? It's perfect. You can pass the bird. Yeah, 0.0071. After sliding to the left twice, are you cool? And now there's a third data set of 238 times 0.9928. I'm going to draw a card. Get to the answer. Cluster 2C4. Just kidding. Just messing with you, man. Just, if I know it messes with you, it's fun to do it. If I call on you, make sure you give me the proper number of digits past the decimal and the proper units. Let's go over to cluster 6. Here's your chance. Cluster 6, seat 5, Aspen. Do you have an answer for me? Dyslexic. Point what? Units, just units.
Wait, oh. Units?
Yeah, the letters that come after it. Look at our previous example. I put letters.
Just from you.
Hey. AMU, you're good. Yeah, AMUs is correct. Yeah, that's exactly what I get too. Yes, ma'am. Yes, for this skill, always 2 digits past the decimal. I'll get it to her. I got it. All right. Let's see if you can do it by yourself. What's your favorite element on the table? Oxygen, obviously. All right, y'all, impress me. Solve the green. Because the data has been altered every year they come out with new data. Yeah, to say that this is more accurate than what I have here. I'm just lazy to rewrite my own questions.
Hello. I mean, it wasn't so fast. I sent a text like a minute ago. All right. I love you. Bye.
We feeling good? Ready for the reveal? Here it is.